All right, so let's get started. Our final exam will be on next week, the same time, Wednesday, 10 to around 11:50. And it covers from the very beginning of the course, lecture 0 to today is what we will stop, like lecture 5. I hope I can finish all the stuff in lecture 5. And then we will not cover the elegance topics, just like in your slides, if it marks as advanced topics, then they will not be in your final exam. And the style for the final exam will be very similar to the midterm. So yeah, that's it. Let's quickly do some recall, and then we will dive into more important part for today, the local structure file system and the virtual file system part. So for the file system, as you know, it's about file and directories. And file is a linear array of files that can be read and written. And for Linux file system, actually, in your disk, each file has their own inode number, and there will be an unique identifier. Or you can think about it just like a unique ID for each file in your disk or in your SSD. And in Linux, actually, there is no difference between directory and file. Directory is also a kind of file. You can think about like this. Okay, and there is a things in Linux is a directory tree. Just like when you are using the terminal, you will say you are going to do the CD. CD is about to change directory to someplace else. So this directory changing is because there is a directory tree inside Linux. So in the very beginning, if you have this kind of backslash, usually it means the root. And then after the root, for each directory, we will use the same backslash to separate each directory or file. Okay, I will skip this part. And then there is a thing that you might heard about is about a file descriptor. File descriptor is more like when you have a process, and this process is going to open a file, and the file can get a number. This number is called a file descriptor. Okay, so it is an integer to identify the open file in all file related operations. So this is very important because this is different from inode number. So this is when a file in a store device and it is requested by a process, then a process will give a number for each file. So for different process, they can give different files, different file descriptors. They're independent. Okay, so it is more like this. So each process has maintained their own file descriptor table. So different process, there is no dependency across their file descriptor table. So let's say like for process A, if process A has like FD2 for a certain inode number, it is possible for process B, it reads the same file with the same inode number, but using different file descriptor. Okay, so this is because they are independent with each else. Okay, so inode is quite different. Inode is a file label. What I mean about a file label is you store something in your storage device, and that things we call it a file. So a file, it has their own inode. So this is a very different idea. One is from a perspective for process, because a process can one of a process can share the same file. Also, a process can open a lot of different files. So they have their own systems to maintain the open file. And the other is about inode. Inode is for maintaining the data you store in your storage device, including hard disk drive, solid state drive, and they're using the inode. So you can think about it, it is more about the position is process and device. So device, file system using inode systems, and the process, they're using a file descriptor. And actually, there is a connection between the inode table and the file descriptor table, as there's an open file table in Linux. So it is about to bridge the file descriptor to inode. Okay. So we also give you two examples to explain about why we need this middle open file table. Why not just using the file descriptor table and just the inode table? Okay, so there are several reasons there, just like because process there is a inheritance when we are going to fork another process, and also there are some shared informations between processes. So because this different reasons, having a middle open file table between the file descriptor table and the inode table would be an easier way to do the implementations. Okay. And we'll also talk about one typical file system called log structure file systems. The background behind the log structure file system is because you guys know for hard disk drive, it is good for sequential access, because for hard disk drive, if you submit the random access, then the time will be super long because you need to wait for the seek time and the rotation delay. So log structure file system is in the edge, like people are using hard disk drive, not in the edge now people are using SSD. So according to the historical background, sequential access is super important. Okay, but if from a Linux perspective, it writes the data to hard disk drive in a sequential order. What do I mean sequential order is, if you are going to write a file, then you submit to say, hey, I'm going to write a file to the hard disk drive, and I will not write the second file until the first file is finished. Okay, but here comes the problem is, if there is no write buffer and your Linux system starts to submit the request to write a file, there is a possibility is, for example, if there is other process that's writing the other files to the same hard disk drive, or there is also the possibility is maybe there is a crash in your systems, then your sequential order cannot be make sure it is in a sequential order. Okay, so a workaround to make sure your data can be stored on a hard disk drive in a strong sequential order, usually we have a write buffer. So we will buffer all the data and the corresponding inode together. So there is also another scenario is, because when you are using a Linux, when you are going to store a file on a store device, it not only stores the file content itself, but also we need to store the metadata, which means we also need to store the corresponding inode to the hard disk drive. So even we can assume this data can be write sequential on the hard disk drive, but the inode part is handled by the file system. So probably between them, if there's no write buffer, it is possible those data will be separate, will be scattered on the hard disk drive. So the performance will be degraded. So for using the write buffer, the goal is to group this data content and metadata together without any accidents. So the second data, we say DK, data K, also is stored with their inode together. After accumulated to a fixed size, we say like 512 bytes or maybe 1 kilobytes. Then the write buffer will group this data into segments and then write them together onto the hard disk drive. And usually this action is all or nothing. What I mean all or nothing is, when the system write the data from write buffer to the hard disk drive and there is a crash, then usually the system will directly mark this is not successful. So the system will not read the data from this part, because all or nothing. So if the segment is not finished, then it will be dropped directly. Okay. So the reason we are going to move inode, we are going to store inode and data together, is because you can think about if this is a hard disk drive and there is a read head, and when a read head 6 or move from A0 to A4, actually, hard disk drive can directly read out all the data required to parse to access DJ, because to access and to parse DJ, we not only need the data content, but we also need the inode to describe about the data characteristics of DJ. Okay. But here comes another question: is how to find an inode in the disk, because this we have 2 inodes now, right? But the question is, if you are going to store like thousands or tens of thousands or even millions of files on this hard disk drive, then you will have a lot of tracks. So where are those inodes that we are interested in? Okay, so that's time I think we also talk about the ancient solution is, let's just put the inode from inode number 1, 2, 3 to maybe n to the tail to the end of the hard disk drive. So each time we only need to know the starting point from the inode 1, and then we know the index of the inode, we can directly get the target inode. So the formula is quite simple. The address of the inode we are interested in equals to the starting point of the first inode number plus the index that we are targeted to get, and multiply to the size, because each inode is in the same size. Okay, because this is a metadata. So this is also related to, if you still remember the slab, inode can be maintained by the slab structure, because all inodes, they have the same size and same structure. So today, if you delete or remove, for example, inode 2 here, then here, if there's another data, it is possible to allocate this inode to a new file. So you don't really need to create inode again, because you have this kind of slab structure. Okay, so inode also come into to interconnect with the step idea in our prior slides. Okay, but actually, sorry, this ancient design comes into an issue is the metadata and the data, they are separated. So at least we need to have 2 access. The first access is to the metadata area to find where the inode is, and the second one would be to get the data. But as you may know, this random access for the hard disk drive, it will take a longer time, because first we need to get where the inode is, and after parsing, we need to wait for the seek time and the rotation delay to get the data. So the performance will not be good. And a better way is the things called a low function file system, just as you already know in the prior slides. We will store the inode with the data together. So inode J will store with DJ. Inode K will store with DK. So in this manner, actually, when the hard disk drive, the read head of the hard disk drive reads from A0 to like A6, actually you can directly read out inode K, data K, inode J, data J in the memory. So CPU can directly process DJ and DK with only using one like seek time. So this performance will be, usually this performance will be like half of the time for the ancient design. Okay. But here also comes a problem is, like we know this is inode J, inode K, right? But because as we said, there will be millions of files. So probably if in this case, we will have millions of inodes now. But where is the location of the inode, right? Because in the ancient design, it is very simple and easy to find where is the location of the inode. But in the LFS, this will be quite difficult, because the inode will be scattered on the hard disk drive. So we cannot, if there is no extra data structure to maintain this inode location, actually, we cannot really get where the location of the inode, of a certain index of the inode. So here comes another design, it's called inode map. So inode map, you can think about is it gathers couple of inode numbers, the address of the inode numbers together. So for example, this inode map from 0 to j, it stores the address of inode 0, 1, 2 until inode j. So this is a summarized data structures. With using this summarized data structure, you can quickly identify the location from inode 0 to j easily. Okay, so the same things, we have 0 to j, also we will have the rest like j to maybe k, and here we have k to n, and so on. Okay. But here comes also a further question is, still we cannot know where is inode map 0 to j and k to n, right? For this structure, it only summarized from 0 to j. So if you can find imap 0 to j, you can find inode from 0 to j in this middle, but we still need a fixed locations. Fixed location is very important in storage device because with the fixed location, we can in advance know, actually, for example, if we have this kind of checkpoint region, we can know, oh, actually, inode map from 0 to j is located on A5, like this, and this K to N is located on like A8. So this checkpoint region, it keeps track of all of the inode map informations in this region. So actually, this checkpoint region, the key idea is very similar to the ancient file system, this one, right? But the difference is, for this one, actually, it directly stores the inode. So each time when we are going to access the data, 100% we need to first access this area. So it will return a longer access latency. And this design, it minimizes the probability to access the inode. Okay, I will not say you don't really need to access twice, because definitely if in the very beginning you are going to access, for example, DJ, so you need to first access the checkpoint region first, and then you need to access IMAP, right? And then you can know, oh, I know J and DJ where the location is, and then you can read them together. So for this one, actually you need to at least two. One is to read out checkpoint region, and the second is to read out from DJ0 to here, A0 to A5. You need to read out the whole region. Okay. So if you only read one data, one and only one, then it will not have a better performance compared with the ancient. It will be very close performance compared with the ancient. Because for this scenario and for the ancient, we both need to read out two different locations. But the thing is, if you have more, I mean, if you have, for example, 0 to j, so if you have j requests and the j requests, they are all inside this range, then you will save a lot, because you only need to read out the checkpoint region one time, and the checkpoint region will be in the memory. So the second time, actually, you just need to access the memory. You don't need to come back to the hard disk drive to access. So checkpoint region and inode map, usually you can store in a DRAM. Okay. So if this is not the first time, actually, you'll be super fast, because checkpoint region and inode map, they will not be too large. Usually they are all summarized data structures, so usually they will only take usually like a couple of kilobytes, then you can store the whole inode information with these two data structures. Okay. But the thing is, if you use ancient design, you cannot store all those kind of things in the memory, because inode also can have some other information. For example, if inode is several hundred of bytes, then if you have million of it, then you will occupy several 10 or 100 of megabytes to only store the inode information. So it is not efficient to store this inode information in the memory. But it is efficient to store this checkpoint region and inode in the memory, because they are all only storing the address of the inode. Okay, so this is about like log structure file system, how it works to handle the performance of reading data from a hard disk drive. Okay, so you may have another question is about how about directory, because in this slide we do not differentiate files and directory, and also in Linux, as we repeatedly mentioned, there is no difference between directory and files. So what about if we are going to access list slash data directory slash DJ? You can think about list D directory is any directory you have in your like computer, and the DJ is the target file you are now going to get. Okay, so it will look like this structure on the hard disk drive. So we will have an inode map, and then inode map, inside the inode map there are two different kind of inode. One is for the D directory, another is for the DJ. Okay, and the inode map will indicate actually DJ, the location for DJ, the location for D directory is on A3 here. And the location for DJ is on here. Okay, so accessing inode map, actually you can get inode, and then getting the inode, you can get the real content of the file. So this directory, the content of the directory is stored on A2, and the content of DJ is stored on A0. Okay. Okay. But here comes another question is about, wait, if we update like DJ, which means if you are going to like somehow like doing some content modification, because maybe this is a Word file or maybe this is a PowerPoint file, so you do some update on those kind of files, right? So if you do some update on those kind of files, then what it happens on a hard disk drive will be like less. Like you do the update on this kind of DJ, probably maybe DJ will become, I'm not quite sure, maybe larger, or maybe there is some content permission changes. So in this case, inode and DJ, because they need to be put together. So if you update DJ or inode, you need to put them together. So they need to move together to some other place. So usually the reason it calls a log structure file system is it will be log at the tail of this, like the prior direct prior position. So if the prior position is here, so you will do a log update. So you will append the data at the tail of the right pointer. Okay. So because the location of the inode J also changes from A1 to A6, right? So the inode map should also be changed, because this one, the prior one is data J is stored on location A1, but now data J after the update, after the update actually is stored on A5, but its inode is stored on A6. So this is for inode, so this is on A6. Okay. Okay, but maybe you have a question, just like, is it possible to remove inode map? I mean, is it possible to just put those information inside, for example, the directory content? So just like this, if you don't want inode map, it is possible, and it is practical also. So the way to do is, we will put the information inside the directory content. So the directory content is here, because this is a directory, so it will maintain about where is the data. Okay. So actually for the inode directory here, you will get like, actually the data is stored on A2. So after passing the A2, actually you will mark about, hey, where is the data? Where is the inode for the data? Actually here, oh sorry, here's a mistake. Here should be A1. Like this is the inode location. So data J is inode will be put on A1. So you will get the same things, like if you get the inode J here, then you can know where is the data, because you can check the INO information. Okay. But the same things, if we do the same update on DJ, so DJ will be updated because DJ is updated, so the INO should be also updated, right? Though, so until now, it's just very similar to what we did when we have the INO map. But because now our information is maintained inside the directory part, so actually we also need to update the directory because the directory keeps track of the information of DJ, right? So now directory also needs to be updated. And then because the directory block is updated, so your INO also need to be updated. So you do one update on only data J, but you update all the stuff related to data J. Okay. And you can think about there's only 2 layers. So if your data is stored on some deeper layers, for example, if you have 3 or 4 layers of your computers to store DJ, then you need to do all the updates from each layer. So it will take a lot of time. But if you have INO map, actually you only need to update the data you're going to update, and then the INO map, then you are finished. So this is the difference between you have INO map and you don't have. Okay. So that is for the good things for using the INO map. Okay. But of course, INO map is not always a good choice. For example, if you use the INO map, which means you sacrifice the capacity because you need another data structure to maintain this INO map. But if you directly include in the directory entries or in the directly block, actually you don't really need too much of extra space. Okay, but because hard disk drive usually offer us a lot of capacity, so people usually pick the upper solutions because the upper solutions even you sacrifice some of the storage capacity, but because for hard disk drive you have a larger, cheaper storage capacity, so people cares more about performance. It doesn't care that much about the. It doesn't care that much about the space. Okay, and I think this is all about low structure file systems. And low structure file system is just a concept. So this is not dedicated design for only hard disk drive. Let's say there are some other storage device or even memory that need to follow the low structure stuff. They need to do the append only operations. Then they still can apply this low structure file system. Okay, so this is just the concept, not designed only for the hard disk drive. Okay, so let's move on to the next topic, virtual file systems. We talked about the low structure file system, and low structure file system help us to map our data blocks, INO, and those kind of metadata together. So when a process is going to read a file, it will access the low structure file system, and the low structure file system will return us where the location of the file by checking the checkpoint region, INO map, and INOs. Okay. So actually, low structure file system is one of the file system among the Linux that you can pick. So for Linux, actually, you can pick some other like EXFAT or maybe ext4, and maybe for Windows, you can pick like NTFS or like some others one. So low structure file systems actually show you a concept about if you are going to implement, if you are going to maintain a file system, what kind of information you need to have. So you can think about low structure file system maintain the minimum stuff you need to have when you are going to build up a file systems. So most of the file systems in Linux, they share the same characteristics. I know there's those kind of data block, directory block structures. Okay, but the thing is, because different file systems, they can support more different functions than low structure file system. Because low structure file system is an ancient design in like 40 or 50 years ago. So after that, there are more storage devices. There are SSD comes. So SSD offers powerful parallelisms, and SSD doesn't really need that strict sequential access. So low structure file system will not really help SSD too much. So some other file system, so like XFS or some journaling file system, which the target is about to make sure the consistency of the data cache. Those kind of stuff, they are not considered in low structure file systems. Okay, but the thing is, because for each disk, or even you can partition the disk into several partitions. Each partition can have their own file systems. So it will be complex if you are going to communicate with each file systems. Even they are doing very similar stuff. Even they have inode structures, and maybe you need some extra parameters to maybe access ext4 or to access other file systems. So virtual file system help to do the virtualization, to do the abstract layer above those file systems. The programmer doesn't really need to understand what is the characteristics of the following file system. Like you are using the ext4, but you don't really need to be very proficient on the ext4. You are using the NTFS, but you don't really need to know a lot about the details about NTFS. And this is all because there is a virtual file system there above them. Okay. So you can think about like this. This is the physical media, including hard disk drive and solid state drive. So above them, we will give it file systems, right? Or maybe you will give it multiple file systems to different partitions. They are all possible. Then for the user side, actually, user usually want it to be simple, compatible. When you are writing your C program, you don't really want to send different C programs parameters. You don't want to customize your write function, for example, to 1, 2, 3, 4 different file systems. So virtual file system helps to bridge this gap. The write function actually will interact with the virtual file system, will not directly interact with the underlying file systems. Okay, so your system write functions in the virtual file system will help you to hook to the file system that the user desire to talk to. Okay, and because we say most of the file systems, they have their own, they have their own design goals, or like they have their own main idea to achieve. But the basic part, usually they are the same. And the basic part, they are very similar to the very typical file system called ext2 in Linux. Okay, ext2 is also used to work as a fundamental structures for the virtual file systems. So the next few slides, when we're talking about the virtual file systems, their data structure and functions, they are all very similar to ext2. Okay. So for virtual file systems, we have 4 main metadata, or you can think about 4 main data structures or 4 main object types. The first is about a superblock object, and I think you are all familiar with this part. Superblock object is about when you are going to create a file system, you are going to mount the file systems, then you need those kind of mounted informations. You can think about when you are using different file systems, you need to know what kind of parameters, or where is the file system mount out, where is the physical disk location, and those are all collected in this superblock object. So the second key things for the file system will be the inode, because for different file systems, they might have slightly difference on their inode design. Okay, so we need to abstract those kind of inode stuff. So there is an inode object. So the inode object, the key idea is the same. We are going to know the informations for the file on the storage device. Okay, but I mean different file system, they can maintain different informations. Okay, and the third one is the entries objects. This is quite trivial. The entries object you can think about is about the directory tree. Okay, because we say there is no directly in Linux, right? Directory is just like an inode, but we still need to maintain the tree, because we need to maintain a hierarchy between the root and what is the next layer of the root and where your data is, which branch it is. So the entry object is about this kind of stuff. So you can look at this example, /user/home/temp. This is a very typical path you will usually see in a Linux, right? And for this path, actually they will have 4 D entries because we need to maintain this hierarchy. So we need to maintain this. This is called the root. We always start from the root. And the user directly. Inside this user directory, there is a home directory. Inside this home directory, there is a file called temp. So there are 4 layers. So we have 4 D entries to describe this hierarchy stuff. And the final one is called file object. So file object represents an open file as associated with the process. Okay. So once again, this is very important. So please bear with me to mention again. So VFS treats directories as normal files. So there is not a specific directory object. They are all maintained by this inode object. And the hierarchy structure is maintained by this D entries object. Okay, so this is important. The entry is not about the directory. They are not different. The entries only maintains the hierarchy of this directory. And there is also one very important stuff is actually the entry objects is not stored on the storage device. Okay, so the entries objects can be created online. What I mean online is when you open your computer and when you start your file system, and the first step you are going to read out any files, right? You'll give a path. Then the virtual file system will help you to resolve the path from a root one by one. And at that time, the virtual file system will access the disk for those kind of idle stuff. So when it starts from the root, you will find where is the inode for the root, and the second layer, where is the second layer of the root. And each time when it successfully finds the inode, the entries will be created. Okay, so we will talk about this later because this is quite important, I think. Okay, so we talk about the data structure part, but data structure only maintains the also like the static part, the information part. But you may know actually in the file system, there is more than data structure because there are some actions. For example, you are going to create a file, you are going to write a file, you are going to read a file, you are going to create a soft link, create a hot link, right? So we need operations. Operations just like actions. So different objects has their own operations. So here come 4 different operations: super operations, inode operations, the entry operations, file operations. So actually they are concepts, they are very similar. What I mean concept is about, they are all about the methods that kernel can invoke on a specific blah, blah, blah. The blah, blah, blah is for a super operation, it will be the specific file system because it maintains the metadata for the file systems. And the inode means on a specific file on the disk or on the storage device. And the entry operation is for the directory entry. So it's about the hierarchical part. And the file options, for the file operations, it is about the methods for maintaining for the open files. Okay. So one interesting thing is about actually this super operations, inode operations, or some Brava operations. You can think about if you are designing your own file systems, you need to hook your own functions with these different super operations. Okay, so you need to customize your file system when you're running a file system, and you need to hook, you need to connect your own file systems with the virtual file system. So the user can interact with your file system via the virtual file system. Okay. So the super block object, we'll go through each object one by one and then to let you get some feeling about what each object is about. Okay. So the super block object, it is designed to store information describing the the file system. So you also call the file system control block. So just like you have a process control block, PCB, right? And the same things for the file system, we also need a file system control block to make sure the metadata inside to describe the file system. And it is usually stored in a spatial sector on disk. What we mean about a spatial sector, you can think about probably it is in the very beginning on a disk or on some very spatial, we already know locations. So this is the reason why we call it spatial. We already know we call it spatial. So it can either in a tail or in a head. They are all possible. So when we mount the file system, a file system invokes a locate-super. So this function reads super blocks on the disk and fills in the super block object. Oh, one key thing to point out is all those kind of objects, they are in the memory because this is virtual file system. So virtual file system, when we are running the stuff, it is about to breach the data on the device and the CPU. So you know, like when you are going to access the data, the final location is the CPU will get the data, right? Before CPU get the data should be in the memory. The data cannot directly to fetch from the storage device. So virtual file system is at this position. Like those kind of metadata part, they are all, you can think about is they are cached in the memory. Okay. So this is super block objects. So inside the super block objects, you can see there are a lot of different information, just like list of all super blocks, identifiers, block size, and the dirty flags, maximum file size, and what is the type of file system. And the key thing actually is the last one. For this super block object, it also contains a function pointer to the operation part. This is super block operations. So those are the collections of the methods this super block object can use to work with the user. Okay, so super block operations, it performs low-level operation on the file system and its inode. So if a file system wanted to write to its super block, then it will be more like this. The super block object will call the super block operations. And inside the operations, actually, there's one function is called the write-super. So like here, there is a function called the, oh, I think I didn't put it, oh, here, sorry. The write-super, so you can update the super block, okay? So the first one is locate and destroy the inode. So it is about create and initialize a new inode object or deallocate the given inode from the memory. Okay, so because inode is strongly related to the file system, so the super block will keep track of this kind of allocation and destroy part for the inode. So when an inode is dirty, actually we can use this function to do the journal updates. This is dirty-inode and then write-inode. The write-inode is about to write the given inode to the disk. Okay, because we say this kind of super block object, inode object, the entry objects, and file objects, they are all stored in the memory. So when they're doing the update, especially for the super block and the inode, it needs to update back to the disk to make sure the consistency part. Okay, so delete-inode is about delete the given inode from disk. So put that super is it calls when among. Among means you are going to remove the file system from the partitions. You are going to make it back to the raw disk, or you are going to switch to other file systems. Then you need to do the among. Okay, so this is the write-super. It is about to updated on this superblock. Okay. So those are all functions that are related to superblocks. But the same things in your exam, I will not ask you about. Please explain about what is the right dash I know. No, there's no this kind of questions in your exam. Okay. So the second one is about the I know objects part. So it represents all the information needed by the kernel to manipulate a file stored in the storage device. Okay. So an I know represents metadata of each file on the file systems, and the I know object is constructed in memory only as files are assets. Okay. So as again, I know is going to as a data structure is stored on the hard disk drive or SSD, and it is going to describe the corresponding file. Okay, this is I know. But I know object is going to, usually it is going to help the VFS to do a fast access stuff. So the I know object can be constructed on the fly and then you just move the data I know from the storage device to the memory, then you will become the I know object. Okay. So actually the I know object part, the data structure part is similar to the I know. So I know we already introduced before. So I just removed the I know object data structure part. I put the I know operation parts here. So I know operations, actually there are several kind of stuff. The first is about create. So create a new I know associated with the entry objects with the access mode. Okay. So this is like you are going to assign about like it is a read or this is a write like file. And then the second one is about a lookup. So lookup is a search directly for an I know corresponding to the file name specified in a given D entry. So this one lookup is quite important because given any file path, how to parse each file path one by one, the virtual file system will iteratively call this lookup to find from the beginning to the tail. Okay, so this we'll have more details later about how to do this kind of lookup stuff. And then next time we will talk about the symbolic link, or you can think about the soft link or the shortcut, they're all the same. So those stuff as here, there is one function about to create this kind of symbolic link stuff. Hey, so make directory, remove directly, the directory is about to create a directory or delete the directory. So remove the directory reference by the entry from the directory entries. Okay. And the final one is quite interesting. It's called rename. So if you using the terminal to rename your file, then there is no function called rename, right? What you usually do in Linux is you use the MV instruction. You use a move to move from one name to another name. So the same things. The idea is similar. For the implementation of the I know operation for rename, actually we will keep track of the old information, the old directory, the entry, and I know part, and then we will replace by the new directory and blah blah. So actually the key concept is to move the file specified by old entry from the old directory to the directory new dash directory with the file names specified by new D entry. So you can think about is actually we replace the old information. We do not just update the file name part. Okay, so we will have more reasons about why the rename is so complex. Why not just like you are using the GUI, just directly modify the name. Actually, GUI is about, it hides all the implementation for the, including Linux or Windows. Like GUI, actually, it doesn't really reflect anything for the low level Linux. Because when you really run the GUI to change the name, actually in Linux, it runs a lot of stuff to make sure it also helps to enable what your change is. Then it includes the rename. Okay. So let's take a 10 and come back later.
期待下，
嗯
因为我作业缴交的时候啊，内容有一点错误的
嗯
还有，然后我又有重写，
嗯
然后我有跟助教也有发信给他的，
嗯，
那会再做重改还是补充的部分？
这不可能看助教怎么做，因为这个作业的那个打分是助教统一他们讨论出来的。
对
对，所以可能要问一下助教他们会。
对啊，
对对对对
我
对。
想说应该可以补交的方式，因为它
嗯
里面有一点写错这样子的，因为我是
嗯
重写这样子。
嗯，对，这可能问一下助教看他们是怎么给分的。对对对对。
谢谢。
我说那个，哦，上次有人问这个，
哦，这是20，就是它是20，然后它就会因为电压高，它就被 drag 出来这样子。
哦，
对对对
好，了解。
对。
请问一下，
嗯
说到说就是 checkpoint region 跟 final map 的这些东西都被存放在 memory 里面，
嗯，
那这个是本来系统设定，就是它在跟 HDD 去做就是连接的时候，本来就会把这相关的资讯，就是除非它是第一次截取，不然它就会把它放在 memory 里面，对吧？
嗯，系统设定吗？因为基本上可以想象成是他在做更新的时候，理论上他就是在 memory 里面做更新的，
嗯
所以反而是他写回来的时间点是什么？因为他如果不做特别设计的话，他就是不会写回来。
嗯，
对，所以他这边才会有，就是这边有说他是周期性的会去做 update。
更新
对，
嗯
当然这个周期性是30秒还是几秒，还是很看是什么 scenario。对，因为确实如果你资料写在记忆体，然后它就直接假设你就直接断电好了，
嗯。
那高级你打一下就烂掉了。
那如果，那我想另外请问的是，说今天是，例如说我们使用一个 HDD 的外接硬碟去，
嗯
就是插在电脑上，然后
嗯
去做读取或者这
嗯
些东西的话，
嗯嗯，
那它怎么样去辨别说相关的这个 checkpoint region 或是 final map 有没有被存在我的 memory 过？
外接硬碟，
对，就例如说我现在插的，然
嗯，
后我读取了这个资料，
你开始读的时候它就开始暂存的。
那所以变成说，假设我再把它拔掉，再把它重新插回去，它会
嗯，
辨识成我已经读过这个相关资讯，还是它会再重新再读一次？
理论上它就重新再一次了。
哦，
对，因为你把除非我就是要看，就是说要做到插回去还是可以，也是可以的，只要它可以确保它的就是 physical address 是一样的，
嗯，
其实是可以做到。对，
哦，
就是技术上我觉得不会有问题，只是要不要去支援这个
这样设定
技术。
的，嗯，
对对对对对，
好，了解，
谢。 All right, so let's come back. So I think there are a lot of questions in the chat box. I just pick a couple of points like people ask more frequent. I think the one that is about the checkpoint durations, like we talk about the checkpoint region, and then in the slides we say for a performance perspective, usually people will set 30 minutes, 30 seconds. Sorry, let me find where is the slides. Okay, here. So yes, so if your crash is smaller than 30 minutes, 30 seconds, so just like if you have a crash around like 20 seconds, then in the low social file system perspective, the checkpoint region is not there. There will be inconsistent between them because you don't really write back the data to the checkpoint region. So that is the case. But you can also think about like this. So current DRAM, usually we have capacitor on it. So even there is a crash, so in most cases, it will not be immediately DRAM will get crashed. They will still have some time for DRAM to write back the data. But how much we can write back depends on the capacity, how large it is. And this is one way you can think about. And you can think about in another way is about usually file system for a consistency part, we will say we are going to lecture all or nothing, which means below within this 30 seconds, it is possible to have the crash. But because this low culture file system, if you set to 30, so which means if there is a crash happens, then after you recover your low culture file systems, it will recognize nothing happens between this 30 within this 30 seconds, which means you will roll back to the prior version. Okay, just like you make the updates within these 30 seconds, there will be drop. Okay, so this is also very similar to the database. So just like maybe you do some extra stuff on the checkpoint regions from now, and then maybe after 2 seconds, it crashed. So your virtual local file system will roll back to the very beginning. You didn't do any update at that time. Okay, so it's still consistent, but the consistency is not what you think about. You should keep track of the latest version. Okay, and maybe you will say, but if you all really want to keep track of the latest version, just like no matter in what timing, then you are going to make sure even even crash happens in any timing, your consistency can always be in a tight match. So in that scenario, you should not use 30 because it will be the trade-off between the consistency and the performance. Like if you set to like 1 microseconds, then this probability will be super low. So actually in the database and the file system, there are a lot of things to talk about the consistency and performance. And I can give you another kind of perspective as because this is local file system, so this is a very ancient design. There is no extra like journaling stuff. You can also think about like if you have the things called journaling, let's say you will always store a copy of the data to the to a spatial. Sorry, let me remove the checkbox. One moment. Okay, so you can think about if there is a thing called journal. Actually, the journal area will be a contiguous area in a disk in some place. So for each operations, you need to make sure the data is first logged into the journal area. Then in this case, no matter what errors happens, what crash happens, you can always make sure your update as in the journal area. Okay, because for each operation, you need to first write a version in the journal area. So no matter in which timing there is a crash, you can always make sure your update is still on a disk. But you need to have some way to recover from this journal area. So there is also this kind of journaling design. But the thing is, you will sacrifice your performance because in this local share file system design, when your update happens in the DRAM, then you will return you finish. But if you have a journaling design, then the true finish time will be your data is returned to the journal area. And the journal area is usually a storage device. So you will take a longer time to wait for the this consistency measure. Okay, so you can think about it just about the consistency and the performance, which side you are going to choose. If you are going to choose a super high consistency, then probably you will sacrifice a lot of performance. And if you are going to choose a super high performance, probably you need to have tolerate to some errors. Okay. So that is, I think there's the most frequent questions have in the chat box. Okay, and once again, actually, even you use this log structure file system, you still cannot avoid to access the hard disk drive on different location twice, because you still need to access the checkpoint region, IMAP and inode, right? And usually IMAP and inode and data, they are stored together. So usually if you are using hard disk drive, you are getting a super large sequential access. So there is possibility for this part, you only need one access. But because the checkpoint region, you still need two access. Okay, but the reason why we have this structure is because if this usage is a long-term usage, not the short-term. What I mean short-term is if your system frequently down, then log structure file system is not a good fit. Because if you always need to reboot, always need to recover, then you always need to read the checkpoint region, IMAP, and like inode. But if you, in a long term, if your checkpoint region and IMAP, they are already in the memory, then in this case, this design will benefit a lot compared with the ancient no IMAP and checkpoint region design. So it depends on the use case. Just like multiple system design, it depends on the use case. So if your use case, for example, is the intermittent, if your use case is an IoT device, your IoT device always will, I mean, maybe in terms of the energy harvesting, or you are going to set power, so your device always down maybe every microsecond level, then log structure file system will not be a good design, because you always need to pay for the overhead to review this checkpoint region, this IMAP in the memory. So you don't really take the benefit from this part. Okay, so this is actually a log structure file system. There are still several issues. It only runs you only runs good in the situation the log structure file system is going to solve the hard disk drive part, like the long-term usage. If you are going to use this for like couple of days or even couple of weeks, then this will be a better design compared with you don't do any IMAP design. Okay. So 1 second, let me move back to, okay. So rename, we will have a deep dive later about what is the detail for rename. Okay. So the entry object. So the entry object is the hierarchical nature of a file system. It managed by the entry object. Okay. So this is what our example, like if we have this kind of path, then we will have 4 the entry objects / home, hello, and world. Okay. So the VFS constructs the entry objects on the fly or on demand as needed. So it performs directly operations, then VFS can construct the entry objects. So which means that the entry object does not correspond to any sort of on-disk data structures. So on-disk data structure include inodes, okay, or data block, directory block, super block. So all those kind of informations, they are not directly connected to the entry object, okay. So you can think about actually the entry object, the hierarchical stuff can be built by checking the data block and derivative block, and inode, the 3 things together. We can construct the hierarchy. Okay. I think this is not quite clear. Let me go back to one slide. Okay. Okay, this one. What I mean is, this is the hard disk drive. So the reason the entry object is created on the fly or on demand is because given this data block, directly block, I know actually it's enough because when you are going to get this path /directory/dj, right? Then the first thing is you are going to find a directory block. And in a directory block, it will indicate us where is the data part. Okay. And then we will also use the IMAP to get where is DJ. So we will get also the DJ part. So you read out this I know directory, and then you read out this directory block. Inside the directory block, it will indicate, hey, actually, there is a thing called DJ inside this directory block. Okay, so for DJ, actually, we can know, oh, actually, the I know is here. Okay, so for this structure, this structure is enough to parse this path. We don't really need to store /d/dj in your hard disk drive. Okay, so let's say if under this directory you have maybe dk, de, df, those kind of stuff, and this directory block, it will maintain like de, df, d, something like that. So traversing the directory block just like to creating the directory entries. But traversing the directory block is on a hard disk drive, so it takes a lot of time. So creating this quick path in the memory is just for caching. It's just for removing the time-consuming tasks to do reading the directory block stuff. Okay, so this is the reason why we say the entries they are created on the fly. Okay, we'll have more examples later. So let's move on. So the entry objects can be in one of the three stats. The first is called a used stat. Use is corresponding to a valid inode and is owned by some like users. Some users is because this inode is about a file, right? So some user is because if you have a lot of process, then they share the same files, then here are the code users. So there's a D count there. The next stat is called unused. Unused is quite also intuitive, which means you have a valid inode, but there's no user. So we just cache it. Okay. And this unused is more like the slab, because for this unused, like if there's some other inodes is going to use this, then you can just copy the information from the storage to the memory. Then that's it. So this can be used like the slab. Okay, so there are also the negative, just like not associated with inode. Either the inode was deleted or the path name was never correct. Okay, so the reason we still store this negative stuff, negative entry object, is because we can quickly respond to the open system call. So when we are doing the open system call, we are going to open a file. Then you don't really need to do a memory allocation because there is a negative position there. You can put your inode from the store device to the memory there. Okay. So both the entry objects and the corresponding inodes can be cached for faster directory lookup and file metadata access. Okay. So the next one will be the operation part. So the operation is about like, actually there's a thing called d-hash. It is about to create a hash value from the given d entry. So the VFS calls this whenever it adds a d entry to the hash table. So in this case, we can use the hashing to quickly find the d entry part. So it is more like you given a file name, a file path. Then after doing the hashing, you can use a hash value to get where is the entry, like that. So you can quickly map with the file name. Okay. So let me pull back a little bit to the prior slides. Rename part. We are going to talk more about rename because rename can help us to bring up the entry and then the inode together. So by Linux, rename is implemented by replacing the old D entry with a new one having a new name. So there are two key things. The one is we are going to use a replacing. We do not really modify the name. Okay, so this is very different from the UI that you are using on the Linux. Because if you are using a terminal, actually you will use the command code, the move command to do the rename stuff, right? And the move command is just like a replace. The second key point is name. So until now, we don't really talk about where is the file name. And the file name is not in the inode. Even you will think about maybe inode is about the file on the storage device. So probably inode will have the file name. No, the file name is not inside the inode. File name is inside the directory part, the directory entry part. Okay. So why not directly modify the name in the D entry? So here are several reasons here. The first one is fast consistency issues as updating the name directory is not atomic. Okay. So here is the directory entries. So the directory entries is the data structure inside the directory block. So you can think about there are two kinds of data blocks. One is for the pure file content. It is called a data block. The other is if you have a directory, then the content of the directory is stored in the directory block. So what kind of content will be stored in the directory? Yes, those stuff. For one inode, we will have one file name. Okay, because you have inode 4, right? So inode 4 is belonging to maybe file 1's file name, and inode 5 will have file 2's file name. And this kind of information will be stored in this directory entries. Okay, so what is the reason not to store in the inode? I mean, why not just put it in the inode? Here's the inode table. You just put it in the inode, then you can store many stuff, right? The reason is the file name is not a fixed name. I mean, you always have different names of your file name. You can have a super long file name and you can have a super short file name, right? But if you look at this inode table, inside the inode table, each inode should be in a fixed size. So let's say if we are going to make sure to keep track of the maximum length for the file name, then your inode will be super large. But the thing is, if there is only one or two files that really used to the maximum length of the file names, then you will sacrifice a lot of space. Just want to make sure your inode can describe a super long file name. And if most of your file name is file name is super short and there's only one or two super long, then you cannot give it a smaller space because each inode should be in the same size. Okay, so if you don't want to waste too much of the wasted capacity to store this file name, a better way is to put to some place they don't really have the big size. And directory entry is a good place because directory entry is part of the directory block. So they just you can think about it just like your file has their own content. Then this is your content. So for a directory, your content, there's two things. One is the inode number. The other is what is the name for that inode number. So in this case, we can solve the problem about the name because you can have your file 1 to be super short name, and you have your file 2 to be a super long. You can have hundreds of characters for the file 2. This is possible in this case. Okay, so this is about the file name. Okay, but file name is not a key thing for this slide. We are talking about rename. So let's come back to talk about the rename part. So the first reason why not directly modify the name in the D entry, because here comes the D entry. And inside the D entry, actually we have the file name and an inode pointer. So it is also possible just directly modify the file name, right? But the thing is about the consistency. Because, sorry. This inode pointer will point to the inode object. So this is the entry and inode object. What is the relation between each other? So with this inode object, actually, there is a thing called data pointer. So your data pointer will point to the location in a patch cache. So the patch cache is also in the memory. It's going to cache the file data you're going to read from the storage device. Okay, and if the data is not in a patch cache, the data pointer will point to the content part inside the storage device. Okay, so data pointer, it depends. If you have already a data in a patch cache, then your data pointer will point to the data in the patch cache. If there's not, then your pointer will point to the content in the data block part. Okay. So because this is not an atomic operations, so updating storage is not atomic. So the failure causes partial result. So what do I mean atomic? Atomic means it will not affected by any crash. So usually atomic is you can think about it's an optimal assumption. Well, when we say we are going to do atomic operation, which means no matter what kind of scenario, no matter what kind of crash, we can assume they will not affect this operation. Okay. But this file name update is not atomic. Okay. Because you update the file name and file name is long. So when you are going to write back to the storage device, this probably apparently is not atomic, because if there is a crash, if there is something else happens, then there will be inconsistent between the D entry and your directory entry stuff. Okay. So atomic is just you can think about it's just an assumption in database people usually use to let you know actually this operations will not be cut by any other reasons. Okay. But for this case now, no, our file name update is not atomic, so we cannot directly do this kind of stuff. Okay, so what we are going to do is we create another D entry inside the memory and we give it a new name. Okay, so in this case, we will write this new D entry to the directory entries. So you will say maybe this is not success, but because this is not success, we can roll back to the prior version. Right, as we say, oh, nothing. So if the new D entry does not specifically write to the directory entries, maybe after writing maybe some time, then there's a crash, then we still can make sure the prior version, I know for point to file one file name, is still there. Okay, so this is the first reason about why we replace the old D entry, not directly modify the new modify the file name part. Okay, so here comes the second reason. Is if the new name is longer and there is no space in the directory block. As we say, the name actually aligned to 4 bytes, but you have like maximum to 255. So you can have a lot of 4 bytes. Okay, so it is possible to like less. If at the very beginning we store the first directory entries here, and then you have the next directory entries, and then the system run a very long time, then you are going to come back to modify one file in this directory. So you are going to modify this name part, right, inside this directory entries. But if your name is not in the same size as the prior, because this is 4 bytes for each minimum granularity. So it is possible, like if you only update couple of characters, then this will not happen. I mean, it still fit in the size. But if you add a lot of characters, or you directly truncate a lot of characters out, then it will probably not align to the same numbers of 4 bytes size. So if this getting larger, then probably it will overlap with your neighbor. So this is another reason why we are going to you can think about just to move to the other place, because it is possible for some cases your name becomes too long or too short, then you are going to move this older directory entries to some other place. Okay, so you need to do the replace. Okay. So this is the second reasons here. Okay. So the the next one is about how to access the /path/q and /file. So the user process, I think most of the things that we are going to do is to access a certain file, right? You have a file and you have a file path. You are going to find where is the data content. This is the most common things users usually do. And given this /path/q and /file, so the first step, VFS parse to get the root, the path, the tool, and the file. So now your VFS gets 4 components, right? And second step, resolve the path for each component. So the first one is root. Usually root will be stored in the cache, so root is quite simple to get. So check whether the entry of the component existing or not. Okay, so the root directory I know is preloaded during system boot. So root, no problem. And then the second one is path. So path, actually, we will hash the path and then to check the entry, to check about, hey, if there is the entry is there already. Okay, so if not, then your VFS will run inode operation.lookup. So inode operation.lookup is here. The label is here. Okay. Here, the second one. So let's look at our description. Search a directory for an inode corresponding to a file name specified in the given D entries. Okay, so this one we can directly check for. One moment. Okay, so we will search path inode from the disk and create the entry. So how to search this inode from disk is, as our log structure file system shows, we will find the IMAP, and the IMAP will find the directory inode. Then directory inode will find the directory block. Inside the directory blocks, they are describing the files in this table. So you can find the file. So for example, you can find, oh, actually the path, and then the next one will be 2, like this. And then you can keep parsing the next table. Like the same thing is you will read out the inode, and then you can read the block, the data block part. So you can finish the traverse. Okay, so same thing, run the lookup function to resolve 2 and file. So after doing this kind of stuff, then you will store the entry for this /path/2 and /file. Okay, so this is about how to resolve the path if the whole path is not in the entry. Okay, so coming back to our very beginning figure, we have file descriptor table, and then there are inode table, and then we have like open file table between them, right? So if you look at this figure again, actually, there is no entry object in the following figure, right? So the answer is, so after a file is open, the file descriptor can directly access the corresponding inode via the open file table. So if you look at the open file table, actually what we log in the open file table is the file offset and then the inode pointer. So with those kind of informations, we can directly get, so where is the inode. So we don't really need the entry object to help to navigate where the inode is. We don't need the path to find in. Okay, so after the file is open, like for the entry object part, we don't need the entry object to find out, so where is the file is. Okay, so the entry object is usually used for file path resolving. Just file path resolving means the process just open a certain file, and we don't really have this file before. Okay, and this is the file path resolving, just like we just summarize the things from the cross slice. So given the file name, and then we have try to check the entry object part, and then if you already finished the file path resolving, so which means you already know this path as this path means you are going to access which inode. Then you don't really need the second time the dentry object because you can directly store the result. You can directly store the inode pointer here to link with the file descriptor. Okay, you already know this path is connected to that file, that inode. So you're finished. You don't really need the entry object again to find out the path. And the entry objects which can be used to find, for example, if you are getting some other path and this path is not resolved before, then you can use the entry object again to find the path and where is the inode. Okay. So the final one is the file object and file operations. So it represents a file opened by a process. So this is very important. File object means the file is already opened by a process. And this is not different. So this is not same as the inode. Inode is to describe the data information on the storage device. Okay. So there may have multiple file objects for the same file. But each file has only one inode and one dentry. Okay, so the reason you can have multiple file objects for the same file is because you might have different permission. I mean, you read all the data from a storage device, but even the same process, you can set it to different permission. Maybe for some reason, one thread is for read, some thread is for write, or like some thread is doing the update stuff. So a certain part it becomes dirty. So there are several possibilities to have, like in the process level, you can have different like file objects that are related to the same inode. But the inode part just means the raw data part. You only have one. There is no second copy. So like the entry objects, the file object doesn't correspond to any on-disk data. Okay, because I mean, you access, if the process create, the process start to access, then you can put in the memory. So before the process access the data, actually there is not information in a storage device because the process is still not start to do anything. Okay, so file system can implement unique functions for each of these operations, or they can use a generic method if one exists. Okay, so this is read and this is write, and read and write is the things you what you image, just like you read the file and you write the file from the process label. But the thing is, because different file systems might have different strategies about reading and writing for different consideration. For example, for XFS, you're going to get a better performance, but for log structure file system, it doesn't really need this parity support. So their read and write, their source code will be different. Okay, but to abstract, to virtualize those kind of stuff to users, actually, you just need to hook XFS read to this file operations, or you are going to hook the log structure file systems read to this file operations. So it depends on which one you are going to use now. Okay, so here comes the polling to sleep, waiting for activity on the given file. Okay, so I believe this is the last file I have. So if we are going to put the file system components all together, then it will look like this. How does the process access a file? So coming back to the very beginning of this course, we have a process, and a process, there is a process control block. And for Linux, the process control blocks, it is called the text structure, right? So inside the text structure, actually there is a field called files. So which means this process has maintained a lot of open files. So these open files are maintained by the file descriptor table. So there is different ID here, or ID 0, ID 1, okay? And the file descriptor table, you will be linked with the file object. So inside the file object, there are so many like icons there, the inode path, and then the entry and mount, this kind of stuff. And for inode and the entry, you can also link to the entry objects and the inode objects for a more fine-grained or detailed stuff what we are going to do. For example, if we don't have a file path, then we will use the entry to construct the file path, something like that. So if you are going to get some more inode information, then you can use this inode pointer to get inode information. So there is also a thing that's called mount, because we are going to know this open file, where is the mounting point of the open file, which means the open file is on which disk or which partition. So for this VFS mount, actually there is a super block. So we can link to the super block, and then once again there is a like the entry here to describe about this kind of the path. Okay. So I think this is all we have for this course. So any questions for today's? Okay, so if there is no questions for you guys in person, then we can just call it a day. So good luck for your final.对，作业表会再更新。
我想问就是，因为他之前说语音储会公开上面什么，那所以在 record path 的时候是怎么样？因为他的情况是什么？
再一次，你说这个就好，什么情况？
就是语音所以它会 on 版上面是吗？
对，
然后所以他在找的时候，他会被公版上面是，然后
就是他在找的时候，其实会是这个会有 DNG，然后这个也会有 这个也会有 DNG，因为它的 DNG会连接这个名字跟那个 inode，这样，所以它其实会维护很多一个一个 DNG。那你在假设你这个是 file path 2这样而已，可是如果你这个里面其实还有 path 里面还有其他资料夹，然后这边还有一个 directory one，然后在这个的话，那你其实前半段不用找了，因为前半段买就用了。这就是可以靠 DNG 去快速的让我们知道前半段是什么。那这个差别是，如果没有 DNG 的话，那你假设你这个 /tab/dire，然后 slash 在一个 file 好了，那你这个 dire 在找的时候呢，你前面这两个你还是要从一叠里面去找 directory block，所以就很花时间。但你今天如果本来先找过这个 path，你要找下个 path 是 /pad/directory one 的时候，这个地方它就可以直接去从 memory 这里拿，因为 DNG 在 memory 里面，它就可以直接把它点击外面找出来。对，
那这样这个 on 版上有什么是什么意思？
就是这里就是应该说不同 process，就是一个 process 它会有自己的 DNG object 这样子。
对，那当这个 process 找这个 file，他会把 DNG 放到 cache，就是 cache 起来，或者是把它删掉。
它会 cache 起来，就是它会把它放在 DB 里面。对，就是它没找完，它越找它的memory 里面的 DNG cache 会越来越多。对，所以之前也有人在讨论说，这个设计其实会，如果你一直不断的去找档案的话，那你 DNG 会越来越多。那你要怎么去做回收这样子？对，因为你就开始占用你的记忆体，那你记忆体就会因为你找了很多档案，所以就渐渐就慢下来，因为系统就慢下来。这样子。对不起，谢谢。
May I ask, do we have a reviewer for the final?
Reviewer?
Yes, do we have a reviewer so we can prepare for the final exam?
Oh, you mean a template?
Yes.
And it will be very similar to the midterm.
It's similar to the midterm.
Yeah, all the structure will be very close to the midterm. The only difference was the content. Yeah.
Is the coverage from the start or from the midterm?
From the start.
From the start.
Yeah, from the start.
Thank you, sir.
我想问，就是为什么 Linux 它可以有相同档？因为我们不是说 Linux 不管后面的是什么副档，
对，
但所以可以有 A.py 或 A.cpp， 但是如果我把那个副档全部删掉，它就说不行，有相同的档案。
因为 A.cpp 跟 A.py 这些对于 Linux 来讲，它就是不同的档案变成。所以如果你把它全部删掉的话，就变成是同一个档案。
可是他不是说他不管后面的 副档是什么？
副档不管后面副档的意思，就是说你打副档的话，对他来讲是他不会知道那是副档的意思。就是你 A 点 py 对他来讲是 A 点 py 这个档案，他不会看你是点 py 什么意思，点也是一个字。对，所以它是你给不同档名，那但对 Linux 来讲，它就是你给不同副档，对 Linux 来讲，它就是不同的档案。
OK，
这样，但他不管你是什么 py 什么，他不会，理论上他不会因为你是 py 就开一个拍档去帮你开。
把它理解成文字。
对。
刚才问的这个 buffer 就是这个部分，它这个 sector 和就我们前面讲那个 HDD 的那个 sector，然后和这里就是说那个 block 和 page 的关系，
sector 是类似的，但是它是不同的东西。就是这个 sector 是或者你可以这样想，因为当初在设计这个 buffer head 的时候，主要大家都是用硬碟，所以它借用了硬碟的字来去做 sector 这件事情。但是 sector 这件事情，不单单指的是硬碟，因为后面又出现 SSD， 所以 sector 这边只代表的是对于软体系统来讲，它可以去定址，就是储存装置的最小单位是什么，也就是它去送回馈之后最小是5 GB。那它刚刚好是把这个档案这个大小跟名字设定成跟硬碟是同样的，去 align 这件事情。对。
那下面这个就是 block，我们就是在 SSD 里面讲，就是 block 下面是 page，然后这
不一样，这里的跟 SSD 都没关系，
只是名字，
他们是名字是一样。对，因为这些系统是就是硬体归硬体，硬体有 page， 然后我们 OS 有 page， 但是他们之所以会用很类似的名字的原因，是因为他们的概念其实是类似的。对，当然他们的大小有些时候是一样，但是他们俩是完全不一样的两件事情。
所以这个这里的那个 file system 的 page 和 block 已经是 OS
了，对。
然后这个
对，没错。所以这跟上面的硬体是完全不一样的两件事情。对。但是因为他们的概念是很像的，就是它都是 partition 过成一个连续的单位，所以大家约定俗成就叫他们叫 page 这样子。但如果你要是认真讲的话，他们应该加个前缀字叫做这个是 OS page， 那 SD 那个叫 name flash page。对。
好的。然后就是这一块就是就是问题是，就是我自己的理解就是它是就是加了一个就其他的这个 path 的这个压使这个其他的 cell 变得透明，就是让它的电流可以通过它。但是你就讲它因为前面就是write 就 program 也是就是用一个20伏的压，然后它就是没有强壮到能使电荷就是进行改变。
对。
那我们这边的 wear out 是
wear out 的意思是，如果你的电荷通过绝缘层的话，绝缘层会被磨损，因为绝缘层是个物质，然后你电子来来回回在那边穿梭的话，绝缘层就会越来越薄。越来越薄的意思就是说，它如果哪天没办法把电子确切的把它关在那个floating gate 里面的话，那就是所谓的 wear out。
那和 retention 不是
retention 是没错，这个概念是很像的。wear out 指的是绝缘层变薄，它没办法去 hold 住电子那件事情叫 wear out。那 retention 的意思是，可是 wear out 有很多种 ，retention 是其中一种会造成 wear out 的原因。retention 的意思就是说，你今天因为电子已经就是绝缘层变薄了，那你长时间使用它的时候，你是有机会会发生 error 的，因为
是发生 error。
对，就是要先有 wear out 的产生，你才会有 retention 的问题。因为 retention 的问题是在探讨说，你假设你的 SD 里面确实有几个 cell 已经有 wear out 的问题了，所以呢，你今天如果放了很久的一段时间，你什么都不去动它，你还是会有资料遗失的风险。那这是因为你本来就有人有 wear out 了。对，它的英国人也是这样子。所以假设你都完全没有人 wear out 的话，那也就代表你不会有人被 retention error 影响，就没有 retention 的可能性。
好。
对。
然后就是这个就是加 vpass 就是它是写入嘛20伏，然后其他是5伏，是为了让其他的不受到这个20伏的影响。
没错，因为他们的导线通常都靠很近，所以20伏它会有这种电场效应，会影响到隔壁的导线。
然后这个1.9就初始的状态是1.9，不是因为它本来在初始的时候就不是0。 就是因为它这边不是写，就是它还没有写入的时候，它就是1.9伏嘛。
对，
那是因为
你说为什么是0伏吗？
对对
哦，因为电子不会完全被抽干，所以它会有一个就是基本的电
在里面。
压在里面。对，
嗯
所以它不会，基本上不会是真的是0伏。对，它这个地方就是相对的，就是它是相对多电子跟少电子的状况。对，但是因为课堂上来讲比较好让大家理解，所以我在图里面都会画没有电子。但因
哦
为实际上来讲不太可能真的到没有电子，所以它就是它实际上它是用，对，它是会有一个，而且它的每一个 cell 的差异会有，也就是说现在看的都只有课堂上都只有探讨1、2个的状况，可能在 SD 里面它是几千万个这样子的东西，那你几千万这样子，你都是用同一套电压去打，因为你本来就很难去控制说你这样子，假设你给20伏特到里面是剩0克还是剩1克还是剩2克还是3克，
哦，就
它是
每
都有可能出现的。
是不一样的，不一定都是1.9。
对，1.9只是想告诉大家是一个相对低的电压值，因为它有可能是它是相对于3伏特这样子。对，但是确实它不会是都是一样的，它都会不一样。
然后老师这个 seek time 和 rotational delay，它是同时进行吗？就是
它可以同时进行，
就是
它可以同时进行。
然后它这个 delay 是因为我 seek 已经找到了，但是我 rotation 还没进行完，所以才会有这个 delay。
对，就是它是应该会找这2个的 maximum，
哦，
看谁花比较久时间。对，
然后老师这一页就是说，因为上一次可能上次课吧，就有个同学问问题，就是说这个 process data 和 fail data，他们俩都会就是产生那个 context switch，但是这个 process data 就产生 context switch 的原因是说，因为它的 data 就是它会先就是如果它不在 memory，它会那个 page fault 嘛，就是说它 context switch 的原因是。就是因为它需要的 data 就没有凑齐，所以它没有进行下一步。
对。
但难道不是？那它就 OS 它不是要处理它这个 page fault，然后去找
我也是对。
那那 CPU 就不管它，就是 OS 去找它的 data，CPU 进行下一个 process 嘛？
没有，CPU 就是在做这个找 data 动作的人。就是 page fault 这件事情 ，CPU 会跑 page fault handler，所以是 CPU 跑这个 page fault handler 去找这个 data 在什么地方。只是说 CPU 找到资料，如果它是在储存装置的话，CPU 就会做 context switch。原因是因为现在 CPU 都有配 DMA，所以 DMA 可以帮你去做剩下搬的动作。如果我今天系统没有 DMA 的话，那 CPU 就要自己搬。对，自己搬就要花很多时间了。对，但一般理论上来讲不会做这件事情，因为自己搬的话，那就是自己搬会有很多议题上面的问题出现。
DMA 搬，然后所以它就是进行到 next process 了。
对，CPU 就跑抗内数据，它就可以去换别的 process 进来跑这样子。对，所以这基本上所有的就是出发点都应该是从 CPU 做什么事情来做出发，因为在整个系统里面只有 CPU 会做事情，其他人都不会做事情。就是其他人都是没有做事情能力的，他就是储存就是存资料，机体就是存资料。
但不是说 CPU 只会直接跟 DRAM 就是进行 store 和 load 嘛？
没错。
其他的都会
没错。
需要 OS，但是如果发生了 page fault，就说明这个资料不在 DRAM 里面。
因为这件事情是这样的，就是说资料不在 DRAM 里面是 page table 会有记录的 ，page table 有个 present bit。present bit 是假设资料在 DRAM 里面，它才会被设起来。如果 present bit 没有被设起来的话 ，CPU 其实读 present bit 就知道资料其实不在 DRAM 里面，然后 CPU 就会进入 page fault handler 去跑这件事情。所以 CPU 会产生 page fault 的其中一个原因，就是因为 present bit 没有被设起来。就是 CPU 里面的 TOV， 他在看，或者是 MMU 都可以，反正他们在看 present bit 的时候，如果他去 check 它是没有被设起来的话，他就会去触发 page fault，然后 CPU 就会跑 page fault handler 来去进行下一步，就是说去确认说这里资料到底在什么地方，到底是有资料还是没有资料。有资料的话是在储存装置吗？还是在什么其他地方这样子？
那 handler 就是
handler 就是一段程式码，然后 CPU 就是跑那段程式码。对。
就交给了那个 AMD， 就交给了刚刚就是说那个会直接处理 memory 和
DMA。那个 DMA 是这样，DMA 也是一个 为控制器，它是 CPU 会去跟 DMA 说你要把资料从 storage 的哪一段搬到机体的哪一段去，CPU 全部设定好之后，它才会做动。
所以 DMA
嗯
DMA 是在 OS 里边。
没有 DMA 是个硬体，就是 DMA 就是小硬体，然后它去搬资料这样子。
哦
你可以想象 DMA 就是一个小的 CPU。
哦，
对
好，好，谢谢老师。
好，谢。
然后请问一下，这张图片就是说，它一次会存 name 和 inode number，然后一次就是如果有 imap 的话，它有办法去存 directory 的，是吗？是存 directory 的 inode。然后如果没有的话，必须每一次都把它会有一整条，然后整个都储存一次。
对，
所以它有2遍。
因为你可以想，就是它如果没有 imap 的话，那你就是这里，像这里，就你要知道下一个人在什么地方，下一个 inode 在什么地方。因为你这边原本 directory entry 里面假设不存 inode 的话，那它可能只存了你下一笔资料叫 j 而已。那这样是不行的。所以基本上 directory entry 里面通常还会再存一个 inode 的资讯这样子，然后以及它的就是 j 在什么位置这种感觉。对，就是它 i 的这里其实比较看怎么实做。这边的话，当初我在想的是，你这边可以直接存 j 到底存在什么地方，就比较简单。但是这样的状况来讲的话，你这个 directory 里面就不会存 inode 的资讯。所以有另外一种可能性，就是你这里面可以存 inode 在什么地方，然后再找 j。对，2个都可以。对，反正这个目的只是说你没有 inode map 帮你，所以你要至少知道你 directory 里面存的这些资料实际上存在什么地方。对，因为你单靠名字是没办法直接知道的。对，就是你单靠名字是找不到它在存在什么地方，它都需要靠 inode 来告诉我们存在什么地方。
那这边有 entry 的作用吗 ？entry
有，这边 entry 用意就是你这边假设你这边好了，这上面都可以啊，这上下都可以。反正你这边找完之后，你不是会知道说你这个 directory 它是对应到哪一个 inode， 然后它里面的人，它里面底下有哪些资料对应到哪个 inode。那 entry 就会把这个资讯把它记下来。那你下次你的 file path 找到这个点之后，你就不需要再到这个 hard 里面来找。就是你的配置是从斜线，然后一个 directory、2个 directory、3个 directory。你到达你前一次存的最远那个地方之前，你都不需要找第10个东西。你就是 entry 在机体里面就有一份就是快取，跟你说这个
所以
这个可以在哪
刚
什么地方。
说这是一个 catch。
没错没错。
那 imap 也在机体里面吗
？imap 不在，
它在
imap 可以在机体里面，但是它在 HDD 上一定要有一份。就是你可以把这个 imap 放到机体，它可以很快速帮你做快取，这是可以的。但是它在 HDD 上一定要有一份，因为毕竟你关机的时候 imap 都不见的话，你这边等于全部找不到了。对，所以你这边都会有个状况是，你关机重开机的时候，它机体是空的，所以如果没有 imap 的话，这些东西找不到的。对，它就变成是需要把 imap 的资讯带到这里面来，所以这边才会出现说这个下面的情形是没有 imap 的状况会长什么样子。
我可以确认一下 imap 资讯到底
imap 就是存
要存什么？
就是里面的它的这个范围里面，它的 directory 跟 file 有哪些人？
这个 file
就是我举例来说好了，如果这个 imap 的设计只为了后面这个档案跟这个 directory 的话，那它只需要存 directory 跟它的 file 的 inode 是多少，就它的那个 address 是多少而已。对，但这个还是很看，就是 imap 要设计成多复杂，就是它也可以就是以 file 为单位的话，那你一个 file 它还有它的 directory， 所以你 imap 就会设计很大这样子。对，所以这个还是蛮看你 imap 的设计是要设计要多大或多小这样子。但 imap 的核心其实就是去把 inode 的这个资讯把它 summarize 起来。
就有点像是这边可能零散一块一块一块，然后我们把它建一个树状结构，然后让 search 它变成更快，
不
联想到一些东西。
有点接近，但是因为这边的 imap 基本上就是只会存，理论上只会存一条线上，就是这个 pad 上面的。对，
就是它把这块组合起来之后，
对，
要 search 里面的东西就不用 sequential，就是
没错，因为你可以这样想，其实 讲课的时候当然是这个方向讲过去，就是 IMAP 啊、inode 跟 data。
嗯，
但实际上它读的时候呢，因为硬碟是 sequential 的，所以你画过去不读白不读，所以基本上它读的时候应该是这边全部都被读出来的。
嗯，
然后这些东西是被读到机体里面，它会开始做 parse 的动作，才会从后面再解析回来说，哦，这是 IMAP，这是 inode，这是 D，这是 D，inode 这是 D。所以你可以想象成说，为什么我会一直强调说，就是这里虽然有多的资料结构，但是它其实不会因为有多这个资料结构而需要你多余的读取时间，是因为硬碟它是这样连续的一直读的。所以就算你今天你只要这些资料好了，那你理论上你的磁头还是会碰到这个，就是你要不要去 trigger 磁头读取这个功能而已。因为你磁头是一直你的读写的盘是，不好意思，你的那个盘是一直不断的旋转，它是不会停的。所以你本来就会碰到它，只是你要不要去 trigger 读这个动作。对，那你一般硬碟来讲，它一定会希望读越多东西越好，因为毕竟你读越多东西，到时候就丢掉而已。总比你下次还再回来读还要来的有效果。所以对他来讲，他其实就是把越多东西可以 group 在一个这个连续的区里面，它是最好的一个 solution。他不在乎有多大，因为它大对他来讲不是重点，因为大的话你就是连续一直读就好了。
那我还有这样，我有疑问就是，如果我既然都读了，那为什么还要 IMAP？就是刚刚讲了 hierarchical search，好像其实没有那么重要，因为我们都读到了。
对，可是好，重点来了，就是你这边这块确实不需要 IMAP，可是你这边有很多块就是你有不同的 file 在不同的地方，但是除非你今天要把整个硬碟全部读完，不然的话，你今天假设你这个 IMAP 是在这个 track， 那个 IMAP 是在那个 track，就你 IMAP keep track on 一个 file path 的资讯而已，但你有不同的 file path 要读，对，所以 IMAP 的功能就会在于你可以去定位到一个比较小的范围里面，然后再把它整个读出来。
哦，所以它又算是一个小 checkpoint。
对，它可以算是没错，它可以算是一个小 checkpoint。
哦，确实，那它了解。你先。
我想问一下，这个 root directory 它被 preload 是会被 preload 到 memory 哦？
对，memory，对，这边在讲的 preload 大部分都是 memory。
那我们在这边 search 的时候，我会从这个DH 然后 path to 然后 file 这样 sequential 去 search。因为有没有可能，其实 file 已经在 memory 了，但我还是要这样扫过去？那我直接去，没有办法直接去查，
可以啊，
有没有在？
有，如果你 file 已经在 memory，就代表这条路你大概已经建好了。所以你这条路的 D entry 应该全部都在了。那如果这条路的 D entry 全部都在的话，那你这边基本上就会是一个 inode pointer 直接可以进在这 inode open file table 里面。所以理论上，如果你这个 file 是在记忆体里面的话，就代表这个 path 你已经找过。这个 path 找过的话，你就是直接查 open file table 就好，你就不用 D entry 了。那 D entry 要什么时候要呢？就是你这边找不到的时候，就是你这个 file path 是新的。所以你这边没有 inode pointer， 你并不知道你这个档案到底在什么地方。那你能够知道，就是你前面可能有一些路径已经找过了，所以你可以从最靠近你的路径再开始找就好了。
所以我会发生的情况是，我的 to 已经在 memory 里面了，但是我 to 没有在 memory 里面，但是 file 在 memory 里面，就是因为可能记忆体满了，我需要清空一些位置，那我就优先清掉。
理论上不会清上面的，但是如果真的发生这种状况的话，那你就一直能找。
就还是要找，
因为他不知道 file 是谁。他不知道，就是对于 Linux 来讲，它不同的资料夹里面都可以用同一个叫 file 的名字。
但它不能存 inode 就唯一。
你说存 inode 吗？
对。
可是他怎么知道这是这个 inode？就是他怎么知道这个 path 是对应到这个 inode？就这个关系在这个情况是没有被建立的。对，就是这个 path 就是for这个 inode 是只有在它确定好之后写到这个 open file table， 它才可以确认就是这个 path 就是配这个 inode。对，
了解，谢谢。
我再问一个问题，刚刚说 entry 不等于 directory 的 ，entry 只是 directory 的 metadata， 你这样想？
我觉得比较好理解是 D entry 比较像是在讲 hierarchy 那件事情。对，因为 directory 是file 的一种，所以它是 inode。然后在 directory block 里面，它有一个比较容易搞混的地方是，它有叫 directory entry 的东西。directory entry 跟 D entry 的效果比较接近。directory entry 讲就是我们就是这个图里面有写，就是它是刚好是讲 inode 对应到的它的 file name 是什么，这是 directory entry。那 directory entry 是拿来去做在 disk 上面去搜寻 配的。就你有这个，你就可以知道你下面有哪些档案，你就可以去一层一层把它解析下来。那解析完的结果可以用 the entry 来去做 cache， 所以它跟 the entry 跟 directory entry 的关联性是在这个地方。
所以 the entry 可以说是 directed entry 复制到 memory 的版本，然后可能再多加点资讯是吗？
就你也可以这样想，
我可以这样想，只是
对
实际上可能
对，实际上它不会是直接就因为毕竟它不会复制，因为它是一层一层找下来，然后可能就是会去第一层确实是没错啊，就如果你只是找一个 directory entry 的话，那没错，就是你说的，它是直接复制上去。可是它还有建立后面的步骤，就是它还有 slash path slash path 2 path 3，就是它有各种 directory，所以它是会建立一整串，然后就建立一个 the entry 这样子。所以它
是一整串，它不是
对，
就是单指这个，就是可能 root 到
它有啊
A 到 B，
有啊，它就会直接这样一个建立下去，
就每个都会是一个 the entry，
每个都会有一个 the entry。
然后每个 the entry 都会是代表 directed entry，
每个 the entry 代表是最后会代表一个 file I know， 就这个 path 的 I know 是什么？我觉得你可以这样想。
这个 path I know
对，但是 directory entry 呢，它不会有这个 path， 因为 directory entry 就是单纯就是这个 directory 的一，对，因为 directory entry 它是需要透过一层一层的 directory entry 去知道它是谁的。因为你那边 directory entry 其实只记住你这一层，可你上层呢？上层是谁？你就要再从别人去领过来，那你这边能只记得你自己这一层，所以你要找下一层的，那你是从这个层去找下一层，所以它没有阶层性的关系，在这个情况上来说的话，我觉得也不能说没有啊，就是说你要自己去把它 traverse， 所以才会有。
所以说 the entry 是一个能够把 directed entry 做链接的版本，
没错，就是它阶层化就是这个意思，
然后它把它存在 memory 里面，
它把它存在 memory 里面，对。
OK， 好，谢谢老师。
我想问一下这个，
你要问上面的
粉红色就是粉红色是它真正的档案吗？
粉红色是真正的档案，对。
可是它不是说它只有一个？
你说上面下面？
都是不是就是它收 links 的话，它不是说只有一个独立的档案吗？可是为什么这个可以对到好几个？
有啊，这里它只有一个独立啊。你看答案出来之后，它就会回到红色，所以这只是一个虚拟的档案而已。就是你的超连接其实就是个虚拟的档案而已。因为你把它删掉了，它就啥事不会发生。对，那它是原因就是因为它最后会把它回到这个地方来，就点回原本的档案。
所以它有3个档案。
它有3个资料块，对，就是它是对，然后这个是一个虚的，所以它就是一个虚的，对，它不算一个档案，对。
那哈令是？
哈令就没有了，哈令就是大家都是 share 同样的资料 ，file content 是一样的，所以它是用计数器来去判断的。哈令比较像是真实档案的备份，但是我不需要去 copy 这个后面的 block。你只会有一份档案，但是呢，大家是用计数器来去做 share。你这边有2个人、3个人都 share 这些档案，这种感觉。
就是名字不一样。
哪一个名字？
是这个啊。
哦，对，名字不一样，对，没错，名字可以不一样，名字可不可以？名字也可以一样啊，但是它就不能在同一个这个路径底下，对，它不能在同一个 directory 底下。你在不同 directory 你要做叫同一个名字，然后用这个都可以。因为这个有一个很关键的用处 ，Harding 有很关键的用处是 backup。你今天想要把你的这个档案的，不好意思，这个资料夹里面的东西全部 backup 到另外一个资料夹去，这时候你就用 Harding，因为你用 Sobling 的话，只要有
什么？这2个字没听懂。
就是备份。你今天想把这个资料夹底下的东西全部备份到另外一个资料夹的话，你就是用 Harding。或者是你想要粗暴一点，你想要把它备份到甚至别的系统上面去的话，那就是用 Harding 来做。
所以这是像复制一样。
你可以想它是复制，但复制它是会真的会变成，就是这个红色变成6份。它这个复制是比较高阶一点的复制，它是用共享的方式去做复制的，你可以这样讲。对。
好，我想问一下这个，有点不太懂这个图。
这个图是这样子的，就是上面的是这个，就是你的资料夹的结构长的样子。就是你的资料夹，假设你这个 root 底下有个 subdirectory 0、subdirectory 1，然后里面还有个档案叫 file 0。那你这个 subdirectory 0里面还有2个档案叫 file 1、file 2，subdirectory 1里面有 file 3。好，这些东西呢，在你的档案系统里面看到的，档案系统在描述的是一个储存装置上面的 layout 长什么样子。所以你看到的会是这样子，也就是说你会有 root directory， 然后呢，这里的每一个资料啊，它其实都是有一个 inode，对吧？我们说每一个都是个 inode，它都是个 file。可是 inode 只记录就是属性这种东西，inode 只是特性而已。你的 raw data，你这个档案真的资料是什么？它是记录在这个 data block 里面的。
哦
你的 raw data 都在 data block。data block 有分2种，一种是 file 的，另外一种是资料夹的。这样，所以 data block 在 file 里面比较简单好理解。你是档案啊，不好意思，你是电影的话就是电影，你是音乐就是音乐，就这样。
嗯，
好，这个比较不好理解的是 directory block， 它在装什么东西呢？directory block 里面是专门为资料夹设计的，它里面装的东西是叫 directory entry， 它里面装的东西就是我这个资料夹底下的档案或者是 directory 它的 inode 的对应关系跟名字，也就是我举个例子 ，subdirectory 里呢，在这里，这个资料夹底下有2个档案，所以我应该要装的 directory content 就是这2个档案的 inode 跟这2个档案叫什么名字，因为这2个档案叫什么名字不会存在 inode 里面，因为刚才说它是因为它的档名的原因，所以它会这样，它就变成是 inode 4对应到 file 1，inode 5对应到 file 2，就这样，它存的是关联性。它存的是 inode， 它存的是这个档案的名字跟它跟 inode 的关联性是什么？
只存这2个吗？
没有，但是方便大家理解，就是简单讲是存这2个，但是其实它不会，但它不会只存这2个，它会存还有存别的，就是辅助的这些资讯。对，
哦，那这个 file 零就不会在里面了。
到你在这，哎哎
file 0
哎，我没画到。
应该也在
好，
所以 file 零就不会在 entries 里面。
不，entry 只会在 subdirectory
对，
里面的。对，
这就是
file 0应该是在这个地方。
它就是一个。
哎，我这边画错了，不好意思，这个是 file 0。
所以它就是一个 data block。
对，它是个 data block，file 0是个 data block，我这边写错了，这边应该是 file 0，这边才是 file 1、file 2。
这边。
对，
这边
就是把这边抽象化出来，变成是资料结构一样给大家看而已。就是每一个档案都会有个 inode， 每个 inode 都会需要有个 d entry， 因为每个有这个 d entry 就可以方便大家，就是有点像是建架那个建那个 hierarchy 的那种感觉。就 d entry 在最 root 的时候，它就只有1个人而已，因为它就只有 root， 然后在第2层的话就有两个。所以你下一次如果你想要去寻找这个资料夹底下的东西的话，你就不需要再去把 file 0在哪里去把它读出来，你就是可以从 memory 知道说，哦，这个人的 inode 其实是谁，就他了，所以 inode 指的是他，你就是只需要把它读出来就可以知道。那你后面你越建越多，假设你今天这个结构不是只有2层，你后面还有一个资料夹的话，那你下次读完这个资料夹，你就可以一次搜寻到这个资料夹是在哪个 inode。你就不需要每次都要再回去从 directory block 里面把资料读出来，然后知道说哦这一层的资料在什么地方，那下一层的资料在什么地方这样子。
哦，
对，这个其实在讲这个，然后后面那个就只是跟大家说，其实每一个档案后面都会有一个 inode 去做对应。那 inode 的用意就是让你去可以知道你的实际上档案存在什么地方，因为你要先查 inode table， 你才可以知道你的 file 1 content 是在什么地方，file 2 哦，不好意思，我刚才再重新补充一下。我这边感觉没有画错，这边只是少画了一个 file 0而已，因为 file 1还是需要有 content 的。对，因为它这个地方只是告诉我们说 file 1的名称跟它的inode 是几号。对，所以这个 inode 4呢会指到这个地方来。对 ，inode 4会指到这个地方来，就是 file 1的 data block 这样。对，
所以这个 inode table 只是它的状态。
对，inode table 只存状态。
然后你要知道它在哪，就要去找这个 directory entries。
不完全，你要知道它在哪，你可以用 inode table 直接找就好。
所以这2个
这2个是
就差不多。
对，
就是
它这边
一样都是就是 table 的关系。
对，它这边只存数字而已，就是 inode 的 index 是多少，这边存比较多，这边会存你实际上档案放在什么地方。就是你需要拿这个数字去换这些资讯出来，这样。因为这边0、1、2、3、4、5这些 inode 是 index， 它是透过这个 inode 4这个 index 去知道说，哦，这是0、1、2、3是这个地方，这个地方读出来，它是有很多各种不同的档案属性，然后档案位置都是记录在这个地方。对，这样。
好，谢老师。
好，谢谢。
老师，就刚刚而言，这个笔记对吗？就是这个是状态， 这个是地址。
不对，这个是资料。data block 存的都会是资料本身，只是对于 file 来讲，资料就是那些你知道的那些资料，就是什么音乐、影像、电影这种的。那这里的资料比较不一样，这里是纯就是档案夹内部的结构怎么样子。这个结构包括了它里面的资料的名称，以及它对应到的 inode 的数字是多少。对，那用这个数字，你可以再回去这个 inode table 去知道说，哦，那个档案放在什么地方，或者是它的更进阶的这些属性是什么，这样。
嗯，老师，这还有一个问题就是，我们这个例子中，那个 driver 是扮演什么角色
driver 吗？我想一下哦，driver 你可以想象成是，看一下啊，这边最后讲了什么 ？Library step physically get。我觉得你可以想成是他在拿这个 staff，他在拿书的时候，他可能需要一些梯子有没有东西，他去拿这种工具类的东西。因为 driver 主要用处就是要去跟这些硬件去做沟通，这些硬体做沟通的。所以它的硬体沟通来讲的话，它的这些协定什么，就是靠这个 driver 去定。对，也就是你可以想想他是怎么去把那些资料拿出来的，就是他要给什么样的资讯这样子。对。
然后就是它这两个 challenge，那么老师用中文帮我讲一遍。
这个是会这讲的是 Barbara Head 的部分。Barbara Head 的原因是因为 Barbara Head 当初在建的时候，你这里一个 buffer 它是一个固定的大小，对吧？那固定大小这件事情就会牵扯到你档案通常都是有可能会很大，所以你一个大档案你可能会需要确认一堆 buffer， 那你一堆 buffer 就会很需要一堆 buffer head， 可是一个 buffer head 它又不小，它一个 buffer head 里面又涵盖这么多资讯，所以今天它第一个问题就是它会需要，首先它会需要先有这么大量的资料结构的浪费，因为你每个人都会需要嘛，它每个人需要它又不小，所以这是第一个。然后第二个是刚才说的，你如果一个 I/O size 是什么4KB 的话，你要先除以512，所以你就会需要有8个 buffer， 所以你光这边的8个 buffer 它就会再加成到这个 challenge one 上面来，所以它主要是2个。
等一下，一我听懂了，是资料结构的浪费；二是
因为它的 buffer 一定是512作为一个 buffer， 所以你今天如果你要读一个档案，这个电影呢是1G 的电影的话，1G 人来算512G 的电影好了，你就会需要有10^9个 buffer head。对，那10^9个 buffer head 呢，其实你就是想要描述一部电影而已，可你莫名其妙就会需要有10^9多少？10亿个这样子的资料结构，就为了描述一部电影。所以他们其实这个意思就在告诉我们说，这件事情其实它并没有让 buffer head 这个设计去理解到现在它是在一个档案系统底下，因为你一般使用者你就是看一部电影而已，看一部电影你就只需要理论上你就只需要一个资料结构就可以维护这个 file， 可是因为 buffer head 当初在建立的时候并没有去考量到这件事情，所以导致它这个 buffer head 它会需要用一堆的资料结构去描述这个档案，这样，因为它是靠那个 size 嘛，那你的512就是一个不一定死东西，所以你档案要是越大的话，你浪费的空间就会越多。
就是还是浪费。
对，2个都浪费，只是不同程度。一个上面是资料结构本身的浪费，以及不弹性，因为后面就讲到说，其实它不需要这样子去记录，它有更好的记录方式。它应该跟配语做整合。那第二个点是因为它的固定的大小导致它的定义 buffer 的方式导致它会在处理大档案的时候会很吃力。对，所以在下一个就是 BIO 状况，它就不是用 size 来看，它是用一个 request。那你一个 file request 可能就是就读一个电影，那你不论你读多大的电影，我都是一个 BIO 就可以结束。对，
那就是说，它第一个是说，data structure 的浪费，第二个是不是配 large block，
不是配固定的 block， 就是这里的 buffer 的定义是，我一个 buffer 就是每512个空间我就要叫它一个 buffer。但是我们在存取资料的时候，其实不是用几个 buffer 来算的， 对吧？你在存取资料的时候，你不会知道它是几个 buffer，
嗯
你只会说你要存电影的这一段到这一段是你想看的电影，但至于这段到这一段，你不会因为它多了一个 byte 少了一个 byte，你就说那我不看这一段了。所以它应该要反过来是用一个 request， 一个 request 就是你想要看这段内容，这个电影的什么部分，它就是一个 request， 它不管 size 多大多小，都应该要可以支援，而且它应该只需要用一个资料结果就可以支援，它不需要去因为你这个 size 而导致你很需要做很多多余的维护这样子。对，
所以第二就是它对于它要读取的资料的大小的范围不灵活适配。
对，这样讲是没错。
好，谢谢了。
好，谢谢。